And chemical is obviously where you use, nasty chemicals that destroy the microbes. So for the rest of this section, okay, up until the next exam, we're going to switch gears a little bit and we're going to focus primarily on how do we destroy microbes. Okay, so this chapter is going to talk about doing it in the environment, but the next chapter will deal with antibiotics, then we'll talk a little bit about diseases, and then we'll talk about the immune system and how we can destroy microbes. Okay, so no more of the really heavy-duty science stuff. Okay, we're going to get away from that. Now it's going to be a little bit more practical, I think, for you guys. So controlling microorganisms has been a problem for since the beginning of man. And as you can see here, this is a guy dressed up in a suit that he would wear to remove dead bodies during the Black Plague. Okay? And this is probably somewhere around 12 AD. Okay? And he was wearing this because it protected him somewhat from the disease. Now, he didn't exactly understand why it was protecting him, but if you look at him, he's covered from head to toe, and this would block the organism from gaining entry to his body. If you look at today, you can see we have a similar kind of getup, okay, except it's a little bit more sophisticated. But the name of the game is the same. We're blocking the organism from gaining entry, and in this case, we're doing that either with Tyvek suits or wearing some sort of filtration apparatus. Okay? But the name of the game here is to prevent the organism from gaining entry to the body. Okay? Now, you can do this by physically blocking, which we'll talk a little bit about. But most of what this chapter is going to focus on is how do we get rid of microorganism primarily by destroying it. Okay? And if you destroy it, then you don't have to worry about these controls because it can no longer cause disease. So this chapter has a lot of kind of boring definitions that we're going to go through. And a lot of these you've probably heard before. Okay? But we're going to expand upon them a little bit and make sure that everyone's on the same page. So first off, let's talk about the different ways of controlling microbes, okay, or different ways of destroying them. The first one is going to be sterilization, and this is the most destructive. Okay, this is where we destroy every single living thing, whether that's an endospore, a vegetative bacteria, a fungal spore, whatever. Okay, but everything gets destroyed in this process. This is used in very special circumstances. Okay, this is what gets done in a hospital, for example, on instruments that are going to be used in surgery. Right, you don't want to have any living things on there, or they may contaminate the patient. But in everyday life, we don't really do sterilization too much. Instead, in everyday life, we primarily do disinfection. And disinfection is where you kill the vast majority of microorganisms, let's say 99.9%, but there's still a little bit that survives. Okay, they're really hard to kill guys, like endospores may survive, or really strong bacteria and things may survive as well. But the name of the game here is to get rid of the most organism possible. Okay? And by doing so, you're going to greatly reduce the risk of that organism causing you problems. You get rid of 99.9% of it, that 0.01% isn't going to do too much to you, okay? In theory. Antisepsis, this is where you do disinfection, but on the skin. Okay? This is a little bit more tricky, since your skin is alive, and obviously you don't want to destroy it. And then decontamination is where you don't necessarily kill the organism, but you get rid of it. Okay? You physically remove it. Okay? So this is where you've got a bunch of shit on the table, and you just scrape it off, and that gets rid of most of the organism. Okay? So how do we go about doing some of these different techniques? Well, we can do it using either physical agents, chemical agents, or mechanical removal, okay, or decontamination. So we'll start off with the physical agents. And here there's two groups, heat and radiation. Okay? Both of these can be used for either sterilization or disinfection, okay, depending on how much you use and at what intensity. Then we'll talk about mechanical removal, which is primarily decontamination, just physically blocking the organism from landing on whatever you're trying to clean. And then chemical agents, this is where we're using chemicals to literally destroy the organism, okay, break it down, so it's no longer infectious. Now, before we talk about some of these different ways of controlling organism, we need to talk a little bit about the organism and how difficult they are to kill. Okay? And depending on the type of organism you're dealing with, you can have different levels of resistance to a lot of these different methods. So some of the highest resistant organisms are going to be organisms that can produce endospores or are prionic in nature. And we've already talked about this. Endospores are very hardy, robust. They're designed so that the organism can survive in very nasty conditions. So you would expect that these would be the hardest to kill, right? we have our moderately resistant organisms. And here you can find things like protozoan cysts, fungal sexual spores, naked viruses, and some resistive vegetative bacteria. Again, though, this is a relatively limited group. Okay? Most organisms are actually going to fit into what we call the least resistant category. And these are the guys that are pretty easy to kill. Okay? Most of the chemicals we talk about, most of the energies we talk about will destroy these guys no problem. So the good news for us is that most organisms are going to fit into this category, which means we can kill them relatively easily. So here we just have some examples of different forms of disinfection or sterilization. And then we have endospores and vegetative bacteria. And what you can see, for example, with heat, you need a lot more heat to kill an endospore than you do a vegetative bacteria. Okay? About 1.5 times more. Same goes for radiation, sterilizing gas, and sporicidal liquids like aldehyde. Okay? So with pretty much everything, you're going to require either more of the compound or a stronger dose of the energy to destroy things like endospores compared to the vegetative. So again, sterilization is essentially removing all living things, okay? Whether that's the vegetative organism, the endospore, the spore, whatever. Everything has to be gone for it to be considered sterile. And sterile just means it's devoid of all life, okay? Again, this isn't done terribly often in everyday life, but in the hospital setting or the dental setting, this is done all the time, okay? Because you really want to make sure whatever you're putting into a patient is devoid of all potential pathogens, okay? Most of the time, this is going to be done using heat. And the heat is going to be moist heat under high pressure. This is known as autoclaving, and again, this is the most common form of sterilization because it is relatively cheap and easy to do. Disinfection, so this is where we're destroying the organism, okay? But there's some that may persist or survive. So not everything is destroyed in this process. Again, this is a way of what we call harm reducing. So you're removing most of the organism, which means it's probably not going to do anything to you. You're kind of hedging your bets a little bit. Most of the compounds, chemical compounds we're going to talk about, are going to be considered disinfectants. And these are the ones that we most often use in the household setting. Okay? So 5% bleach, boiling water, iodine, and so forth. Antisepsis, so again, this is removing organism from living tissue like the skin. Again, this can be a little bit more difficult just because your skin is relatively sensitive, it's alive. And so if you're putting really nasty chemicals that kill microbes, you may also damage your skin at the same time. But there are compounds available. Most of these are going to be iodine in nature or chlorhexidine in nature, and they work pretty well. The name of the game for using things like antiseptics, which are chemicals that destroy organisms on living tissues, is to prevent something called sepsis. And sepsis is where you have microorganisms growing in tissues and in the blood. This usually results in a very serious illness for the patient, and so this is why we try to prevent this as much as possible. Any technique to prevent sepsis is known as asepsis. So this is where doctors will scrub up, wash their hands very well, put on gloves and things. That is a process of asepsis. It's reducing the amount of organism on your skin so you're not transferring it to your patient. Now, generally speaking, if you see a word with "side" at the end, that denotes that agent or chemical destroys and kills the microbe. Okay? So if you see bactericidal, this means it kills bacteria. Fungicidal kills fungi, virucidal kills viruses, sporicidal kills spores, and germicidal or microbial kills most germs or microbes. Okay? Conversely, if you see stasis or static at the end of the word, that denotes that it doesn't necessarily kill the organism, but it stops it from growing, okay, or dividing. These tend to be much more milder compounds, and a lot of times they can actually be used in food items and ingested by humans without much problem, and so these are what we often call preservatives. They're designed to not kill the organism, but stop it from growing so that it doesn't take over the food and cause it to spoil. Okay? So bacteriostatic or fungostatic, microbial static, again, anything with static or stasis lets you know that it stops growth but does not kill. Decontamination. So again, this is where you're just physically removing the organism. Okay? But you don't necessarily need to kill it, but if you kill it at the same time, it's usually better. And sanitation is where you are killing and removing at the same time. Okay, so you're getting kind of the best of both worlds. To do this, we often use chemical compounds called sanitizers. Okay? And once we use a sanitizer on a surface, it is then considered sanitary. Okay? So again, a lot of just basic definitions, most of which you've heard of before. Degermation is a similar process, okay, where you're just physically removing the organism, but instead of it being on an inanimate object, it's on the skin. Okay? So an example of degermation is washing your hands. When you wash your hands with soap, you're not really killing the organism, you're just scraping it off your hands and washing it down. Now, before we talk about some of the specific ways to kill microbes, we need to think a little bit about what type of microbe we're dealing with and how we can actually get rid of it, okay? And what type of method would be best to do so. Now, a lot of this stuff you guys will probably never have to think about in the real world, okay, especially in a clinical setting. And that's because there are plenty of people behind the scenes in the hospital that will figure all this crap out for you beforehand, okay? But the reason why we're talking about it is so you can get an idea of what it takes to really understand how to destroy and get rid of microbes, okay? Especially really hard to kill microbes like C. diff, for example, okay? So, first off, whatever you're dealing with, does it need to be sterile or is disinfection adequate? Okay, 9 times out of 10, disinfection is all you really need, okay, unless you're putting it into a patient. Is the item to be reused or permanently discarded? And nowadays, most things are going this route. Okay, if it's permanently discarded, then you use it once, get rid of it, and you don't have to worry about cleaning it up. If it does have to be reused, though, can it withstand heat, pressure, radiation, and chemicals? And that's because these are the items used for sterilization. If it can't really withstand these, then it's not going to be able to be sterilized. Is the control method suitable for the given application? If you need to use some really nasty caustic chemical and it's something you're then going to put into a patient, it's probably not ideal because there's probably going to be some chemical that gets carried over. Will the agent penetrate to the necessary extent? It's a very porous thing. You got to really think about, is it going to get through and kill everything in there? And is it going to be cheap and labor efficient? So these are some of the practical things that have to be thought of before they put these into place in the hospital setting. So what exactly is microbial death? Well, it's relatively simple. It's where the organism dies. Okay? And by die, I mean it stops growing and it is destroyed. Okay? It can no longer become metabolically active. It can no longer do whatever it needs to do as a microbe. Okay? But again, there is the possibility of not necessarily killing the organism, but stopping it from growing, okay, and that is different than death. The organism is still alive, it just can no longer divide. Now, what can affect how quickly a microbe dies? Okay, there's a lot of things involved with this. Well, first off, the number of microorganisms present. If there's more organism present, the longer and harder it will be to kill them all. Okay, again, common sense. The nature of the microorganism in the population. If it can produce endospores or it's a very hardy, resistant organism, then obviously you're going to need to use more chemicals or more energy to destroy them. The temperature and the pH of the environment. This is especially true when you're dealing with chemical compounds, because some chemical compounds are denatured at certain temperatures or pHs, so they may not work effectively. The concentration of the agent that needs to be used, and then the mode of action of the agent. If the agent is targeting, a cell wall and your organism doesn't have a cell wall, it's probably not going to work well. And then the last bullet point is relatively important, and most people forget about this. The presence of solvents, interfering organic matter, and inhibitors. The key thing for you guys is this interfering organic matter. A lot of the chemical compounds we're going to talk about, one in particular, sodium hypochlorite or bleach, gets inactivated very, very, very easily with inorganic matter. And by that, I mean, shit or patient tissue. And so if you pour bleach on it, and if there's a lot of this interfering organic matter, it may inactivate the bleach before it actually is able to, decontaminate and disinfect your item. So this is just putting everything into a nice little graphical form. So up here we have 10 to the 9 organisms, so a lot of organisms. And you can see once we start our sterilization, For this particular organism, it takes about 13 minutes for it to all be destroyed. Okay? And as we mentioned before, the more organism you have, the longer it takes. The lower organism you have, the shorter it takes. Okay? And this all kind of makes sense. Vegetative organisms tend to be easier to kill, so they usually require less time before they're all destroyed. Where spores are much harder to kill, and so they can stick around for much, much longer periods of time. And as we mentioned before, if you have a microbial compound, it will kill the organism, so the amount of organism left in the material is decreased. Where if it's a static or stasic compound, instead of killing the organism, it just maintains the same level of organism without letting it grow and divide and continue upwards. So how exactly do a lot of these compounds work? What do they target within the cell to destroy it? So there are 4 areas that these can work in, and these aren't mutually exclusive. So that means some of these chemical compounds will hit all 4 of these at the same time, right? It really just depends on the compound itself. So you can target the cell wall, the cell membrane, protein or nucleic acid synthesis, and then finally protein function and folding. So the cell wall is a nice target because the cell wall is important for a lot of bacteria. Okay? Without the cell wall, the cell quickly explodes or lyses. So you can add in compounds that will eat away at the cell wall or digest it, and this allows for the cell to basically explode and die. Okay? These work relatively well with gram-positive organisms, but with gram-negative organisms or mycoplasma, it may be a little bit more difficult to use these guys. You can target the cell membrane. So the cell membrane is made out of phospholipids, and these lipids can be broken up using something called a detergent or surfactant. Detergents are designed to kind of grab onto these lipids and then make them hydrophilic or dissolve in water, and this will disrupt the membrane and kill the cell. So remember, cells or cell membranes are very important for the cell because it allows the cell to control its environment. So if these are destroyed, it can no longer do this, and it then quickly dies. Okay? These are often called soaps, and so this is one way that a soap can help kill a microbe if you're washing your hands or dishes or what have you. You can target the protein or nucleic acid synthesis. So if you stop DNA replication, RNA transcription, or protein translation, the cell will then quickly die. Okay? The reason for this is the cell needs protein. And all of these are essentially important for the eventual production of protein. Now you can do this in a couple different ways. There are compounds that will destroy the ribosome. Once the ribosome is destroyed, then it can no longer translate into protein, the cell dies. Or another common route of destroying the organism in this way is using something called a mutagen. And we talked about mutagens a little bit in Chapter 9. These are chemical or physical energies that induce mutations in the DNA. And if you get a lot of mutations in the DNA, then when it gets transcribed and translated, the proteins are all weird and funky, and then the cell quickly dies. Lastly, protein function. So proteins in the cell, as we've talked about before, are complex structures. Okay? They're kind of long strings that are wrapped around themselves and form these big kind of 3D structures. So one way to potentially kill the organism is to denature or unravel these protein structures. Okay? A lot of the compounds we're going to talk about today work in this method. Okay? This is by far the most common approach. So all you have to do is get the compound in, it unravels the protein. Once the proteins are unraveled, the cell no longer functions and dies. Another added benefit of going this route is that once all these guys are unraveled, they will get kind of tangled up with each other, and this creates kind of a gummy mess inside of the cell, again, forcing it into death. So let's talk about some of these controls that we can actually utilize. The first group of controls we're going to talk about are the physical controls. Okay? And this is using some sort of physical energy. And the most common are going to be heat or radiation. Okay? So we'll start off with heat, and that's because this is by far and large the most common approach that is used. Okay? You can use 2 different flavors of heat, moist or dry. Moist heat is exactly as it sounds. You have heat with water. Okay? This allows for coagulation and denaturization of those proteins. And when that happens, the cell then dies. Conversely, you can also use dry heat, and dry heat basically dries the organism out or incinerates it or catches it on fire, and this then kills the organism. Okay? Both of these methods work. However, moist heat is by far more energy efficient and cost effective. Okay? So it is the one that gets used most often. So here we have one organism that we're killing with both moist heat and dry heat. And what you can see is that with moist heat, if I try to kill my organism at 121 degrees Celsius, it takes about 15 minutes to reach sterilization. Conversely, with dry heat, using the same temperature, it takes about 600 minutes. Okay? So it takes much, much longer with dry heat, and it's much less energy efficient. So again, this is why it doesn't get used too often. However, there are some instances where moist heat isn't that great, and that's because it can disrupt or break, sensitive pieces of equipment that are very thin and fragile. So in that case, then we would have to do dry heat. By far and large, you're going to pick moist heat if you can because it doesn't take that much time. Now, as we've already talked about, when we're trying to destroy microorganisms, we have to think about the organism and its resistance to some of these different methods. And for temperature, the hardest thing to kill with temperature is going to be the endospore. Okay? And this is kind of true with all of these different compounds and controls. And the reason the endospore is the hardest to get rid of is because it has those multiple layers that surround it. And this protects it from things like extreme heat. However, if you have extreme heat with water, once you heat up the water, these water molecules become very energized, and they then can bombard and break through those layers in the endospore. When this happens, the endospore then dies. Okay? So these are going to be the hardest guys to get rid of, but we can get around that by using moist heat. Okay? Vegetative cells tend to be very easy to kill with heat. Okay? You can heat them up below boiling even, and that will kill most of them. And viruses in particular can, if they're naked, are very resistant to heat. But if they're not naked, meaning they have an envelope, they are pretty sensitive to heat. Okay? Even just a little bit of heat will destroy them. Now for each organism, there's two things that we can calculate. The thermal death time and the thermal death point. Okay? Again, this is something you would never have to do in your guys' line of work. But behind the scenes, this is something that gets done with really difficult and hard to kill organisms so that we understand what is the bare minimum amount of heat and time to destroy that organism completely. Okay? So the thermal death time is the shortest length of time required to kill all organisms at one temperature. Okay? So I pick one temperature, let's say 121 degrees, and then I heat the organism up, and every minute or so I check to see if everyone's dead yet. Once everyone's dead, that tells me that's how long it takes to kill everyone at that time. The thermal death point is the lowest temperature required to kill all organisms in 10 minutes. So here I have my organism and I expose it to multiple different temperatures, wait 10 minutes, and then I look to see which one caused all the organisms to die. Once I have both the thermal death time and the thermal death point, I can cross-reference these, and I can come up with the most effective temperature at the least amount of time to kill all organisms in that case. Okay? Again, something you guys would never have to do, but it is something that gets done when you're first trying to eradicate an organism or destroy it, so you can get a good idea of what is required to do so. So let's talk about some of the different types of moist heat that can be used. Okay? So steam under pressure, non-pressurized steam, pasteurization, and boiling. We'll start off with steam under pressure. Steam under pressure, also known as autoclaving, is probably the most common form of moist heat used for sterilization, okay? Especially in the clinical world. This is where you take your instruments that you want to sterilize, you wrap them up, and then you stick them into your autoclave, which is basically a big pressure cooker. It has a chamber that you seal off, and then you pump in hot steam. This steam is usually at about 121 degrees Celsius. This is 21 degrees above boiling, and at 15 psi, pressurized. As we mentioned before, this will break down that outer coating on things like endospores and make it easier for them to be destroyed by this process. The reason why this is the most common approach is because it's pretty cheap to do. Okay? But the problem with using autoclaving is that it also causes can do a lot of disruption to the instruments that you're trying to sterilize. So if it's very thin or electronic or plastic or something like that, it may get warped and weird inside of this guy. So this works well, it's cheap, but you need to make sure that your instruments are stainless steel or heat-resistant plastic, or they will get destroyed. Non-pressurized steam, this is primarily used as a form of disinfection. Okay? So it gets rid of most organisms, but not all. However, you can sterilize with non-pressurized steam as well. This is a process known as tyndallization, but this is a very inefficient and it takes forever to do. Okay? So it's not something that gets done a lot. Traditionally, this was used a lot in canning and kind of preserving beverages. So what you would do is you would take your beverage, you would boil hot steam through it. This kills most of the organisms that are vegetative. However, endospores will survive this process. So then you set it out at room temperature for 24 hours. Those endospores wake up, start to grow again. Then you put your steam through, and that kills most of them. Okay? But some still remain as endospores, so you do this one more time. So it takes 3 cycles, and each cycle takes about a day and a half. And not only does it take a while, when you're boiling hot steam through your liquid, it's going to cook your liquid, okay? And if that's a beverage, it's probably going to make it taste like shit. So this isn't something that gets done very often anymore. But back in the good old days, before they knew any better, this was the most common approach. Pasteurization. So pasteurization is where we disinfect a liquid, okay? This is not sterilization, this is just disinfection. The way that this works is we heat our liquid up to a temperature for a certain amount of time, and this gets rid of most organisms. Okay? But endospores and resistant vegetative bacteria will not die in this process. Okay? Now, the reason why this doesn't sterilize is because we're not heating it up to a sufficiently high temperature. Okay? But the reason we do that is because if you do heat it up to a really high temperature, your beverage will change. Right? It will boil. If there's sugars in there, they will get all screwed up, they'll caramelize, and that will cause different tastes to the liquid. Okay? So instead, we heat to a lower temperature, and we can do this in one of 2 ways, either the flash method or the batch method. Flash is where we heat to 71.6 for 15 seconds. Batch is where we heat to 63 to 66 for 30 minutes. Okay? Both of these achieve the same result. You lose 99.9% of your organism. However, this one's quicker, and this one takes longer. So why would we even do the batch method? Well, because we're not heating our liquid up to a high enough temperature to allow for something called the browning reaction to occur. Browning reaction is where you can change starches into sugars and sugars into caramelization or carbon. And if you do this to a liquid that you want to preserve the taste in, it will change the way that it tastes. An example would be milk. If you take milk and you do the flash method, it tends to get a sweeter kind of caramely taste. In Europe, they do it, they don't care, they drink it, it's fine. In the US, we're more finicky, so instead we go this route. And by going this route, our milk tastes more like it should, right? Like it came from the cow. But it's important to note that it does not kill all microorganisms, okay? It does not sterilize the liquid. This is why even though all of our milk is pasteurized, even though it's been pasteurized and most organisms have been destroyed, if we put it in the fridge for long enough, it will eventually spoil. And that's because the organisms that did survive, usually endospores, can wake back up, start to grow, divide slowly in the cold fridge, release acids, and this curdles the milk. So it does not sterilize, but it does help preserve the liquid for longer periods of time. Boiling water. So boiling water is another form of disinfection. This is not a way of sterilizing. Okay? A lot of people tend to think this is a way of sterilizing. If you take something and you boil it for 10 minutes, it is not sterile. Okay? Just make sure you keep that in mind. Endospores survive this no problem. In fact, there are a lot of bacteria that can survive this no problem. And that's why it often takes 30 minutes before you can reach pretty good amounts of disinfection with boiling water. Okay, so that's moist heat. What about dry heat? So as I mentioned before, dry heat works, but it's not very energy efficient. It usually takes much longer, okay? So this is typically only done in special circumstances. One important place this gets done a lot is in the microbiology lab, okay? How we sterilize our loops by heating them over a Bunsen burner until they turn cherry red is a form of dry heat sterilization. We are heating our organism up until it catches fire or incinerates, and then it dies. Okay? But if you tried to do this, on a large scale, it would not be energy efficient at all. So we don't do it too often. The other form of dry disinfection or sterilization is using a dry oven. This is where you heat the organism up to 150 to 180 degrees Celsius for 2 to 4 hours, and this will get rid of most organisms. Okay, but it's not very good at sterilization. Again, this is typically only done on very special pieces of equipment, so very thin pieces of glass or certain metals that can't go into an autoclave because they'll rust. But generally speaking, this isn't done too often. So we've talked a little bit about heat. Now what about the opposite? What about if we cool the organism? Well, cooling the organism, or desiccation, which means removal of water, actually aren't really that toxic to the organism. Instead, it's thought of as more of a static approach, which means it doesn't kill, but it stops the organism from growing. Okay? So when you chill the organism down, it slows its metabolic rate, and if you go below freezing, it stops metabolism altogether, okay? Unless it's a very specialized organism. So this is why if we take our chicken and we put it in the freezer, it can stay in the freezer indefinitely without being spoiled. Okay? It will get frostbitten, which is nasty, but it's not going to kill you. Okay? It's not an organism. And that's because in the freezer, it just stops the organism from growing altogether. But it's important to understand that it doesn't kill the organism. And this is why if I take that chicken out of the freezer, throw it on the counter, and walk away for 2 weeks, it will still grow and get nasty with all this bacteria. The bacteria was already in the chicken, and it just woke back up once it warmed up a little bit, and then just started growing and dividing and ruining food. The same goes for desiccation. So where we remove the water in kind of a slow way, not boiling or not incinerating it, but instead just slowly remove the water, this does not kill the organism. Okay? Instead, it just puts it in suspended animation. In fact, if we do something called lyophilization, which is freezing and removing the water at the same time, we can actually preserve organism. So if we do this on bacterial colonies, we then can ship these bacterial colonies as a dry powder, and someone could then pick that powder up, add some water nutrients, and bing, bang, boom, they start to grow again. Okay? So it doesn't kill either of these approaches, it just slows their growth. Okay. So the next type of physical energy we can use to destroy organism is something called radiation. And radiation is where you have particles that are emitted, okay, either neutrons or electrons, that bombard the organism and disrupt their DNA. Okay? And when you disrupt their DNA, this usually causes mutations, and then the organism eventually dies. Now there's 2 flavors of radiation, ionizing and non-ionizing. Ionizing radiation is where electrons are released, and because these are much smaller, they can go through the cell, and they can literally chew or break the DNA up into chunks. Okay? This type of radiation is often called a penetrating radiation, and that's because it can penetrate through pretty much everything, except for really electron-dense things like lead, for example. Okay? The other type of radiation is known as non-ionizing radiation, also known as UV light. This does not penetrate, okay, so it's just whatever the light can go through, and then that's it. And this works, instead of chewing the DNA up into bits and pieces, it actually fuses nucleotides together, and this induces mutations. Okay? So both of these result in cell death. However, this one tends to be way more potent than this one. So non-ionizing isn't the greatest, but it is better than nothing. So let's first talk about ionizing radiation. So ionizing radiation can occur with gamma rays, X-rays, or cathode rays. By far, gamma rays are the most important, and that's because these have the smallest wavelength, and that means they can penetrate most things very, very, very well. Okay? These gamma rays, when they're used for ionizing radiation, is one way that we can go through a process called cold sterilization. This means you can sterilize something without using heat. So what you would do is you would take your item, you would stick it in a gamma radiator, basically a microwave on steroids, and you would zap it. Okay? This would penetrate all the organisms, chew up their DNA, and then they would die. This requires about 5 to 50 kilograms, depending on the type of organism you're trying to destroy. So it needs relatively high doses. And the really cool thing about using gamma rays is it's very penetrating. Okay? So what you could do is you could take all your stuff that you want to gamma radiate. You could pack it in bags and boxes like you're going to ship it. And then you just shove it into a large gamma radiator, push a button, come back, and everything's sterile. Okay? So it's very effective in that way. But the reason why this doesn't get done on a wide scale is because it's very dangerous. Gamma rays are the ones that you think about when you hear about, like, nuclear disasters, nuclear bombs, Chernobyl, that kind of thing. These are the ones that, if they get into you, are going to cause cancer in low doses or radiation sickness, which is deadly in high doses. So again, it's not something we use a lot because it is relatively dangerous. Also, the machines required to make gamma rays are very expensive, okay, and require a lot of oversight so that they don't get misused. So where do we utilize ionizing radiation? Well, it gets utilized a lot in food products. Okay? A lot of food products like raw meats will actually go through a gamma irradiator. Okay? This will get rid of a lot of the organism in there that may cause disease. However, it's done at a very low dose, so it's not going to sterilize the food, but it is enough to get rid of most of the bad guys. Medical products that are sensitive to heat can be used in a gamma radiator. And again, it's relatively fast, has penetrating power, and no heat is used. But it is dangerous to use. Non-ionizing radiation, also known as ultraviolet radiation, is essentially ultraviolet light. Okay? Ultraviolet light has a 254 nanometer wavelength, which means you can see it kind of with your unaided eye. And because it is light, it does not penetrate opaque objects. So if I was using a non-ionizing radiator on this table, it would just get the surface. It wouldn't go all the way through the surface, down to the floor, and into the carpet like an ionizing radiator. So, and because of this, it's not the greatest at getting through really difficult organisms like endospores. So it works well for a lot of vegetative organisms and viruses, but endospores, it doesn't really penetrate well, and it doesn't really kill that well. Okay. How does it work? Well, ultraviolet radiation works by creating what we call pyrimidine dimers. This is where in the sequence, if you have A's and T's next to each other, when you expose them to UV light, they fuse together. This then causes an error in transcription and translation, and then the cell dies. Where does this get used in the real world? Well, you can use it to kind of sterilize the air. So in places like hospitals and fast food restaurants, you may have noticed this like weird looking light that comes off and shines a blue light. Well, that's just shining UV radiation, okay? And any particles that are flying around can be exposed to that and potentially destroyed. Another place this gets used a lot is in water treatment plants. Because water is transparent, you can shine the UV light and it penetrates relatively well. Okay. All right, so that's enough of the physical energies. Now let's talk about decontamination, or physically removing the organism. Now, on a solid surface, this would literally just be scraping it off, right? So wiping with a towel or washing your hands or something along those lines. For liquids and gases, though, we have to do something called filtration. And this is where we take the liquid and gas and we pass it through a filter. And a filter is just a membrane that has really tiny holes, or what we call pores, in it. These pores are large enough to let the liquid or gas through, but small enough to where infectious things cannot pass. Okay? So once you pass your liquid through the filter, everything that comes out the other side, in theory, is sterile. Okay? However, there's one big exception to this. Viruses can easily get through these pores. So it gets rid of bacteria and spores and fungal organisms, endospores, whatever. Okay? So it doesn't work well with viruses at all. Okay, so now let's talk about the last group of control mechanisms, and that is chemical compounds. This is probably the largest group and the one that most of us think about. And that's because these are relatively easy to use. Okay? There are over 10,000 different antimicrobial chemicals, agents that are available, and we use about 1,000 of them in everyday life. Okay? So they're very, very ubiquitous. And a lot of times you use these and don't even realize you're using them. Okay? They can be liquid, gaseous, or solid. If they are dissolved in water, we call this an aqueous solution. If they're dissolved in alcohol, we call this a tincture. Now, designing and figuring out what type of microbial cytochemical you want to use is a relatively difficult thing. Okay? And that's because they all have their pluses and minuses. However, ideally, you would want them to have all of these properties. I can tell you right now, there's no chemical out there that has all of these properties. Okay? So you always kind of have to figure out what's best for my situation. Right? Is this chemical going to get rid of the organism I'm trying to kill? Is it going to destroy whatever I'm trying to disinfect? Right? All these things have to come into mind when you're developing them. Before a chemical agent to work well, you obviously want it to have rapid action, even in low concentrations. And the reason for that is these tend to be toxic to humans as well. So the lower the concentration you can use it, the safer it probably will be for you. It should be soluble in water or alcohol, and that's because, again, these are relatively safe for humans. If it's in toluene or some other weird solvent that's dangerous to humans, it's probably going to cause more harm than good. It should be broad spectrum, kill most microbes. It should also be able to penetrate surfaces, right? Because that's usually where it's going to be used. Organic matter shouldn't really affect it. However, again, a lot of these compounds are affected by organic matter. And ideally, you want it to be non-corrosive and non-staining, but again, that's difficult to come by. Hopefully, it would sanitize, which is, will help remove the organism, as well as deodorize and make it smell better. And it should be affordable and readily available. Again, impossible to get one compound that does all of these things very well. So here are some of the different agents we're going to talk about, okay, in today's class. What we're going to do is talk about the main reactive group on that agent and briefly how it works, okay, and then where we use it and find it in the real world. Again, when you're developing these compounds or determining what type of compound to use, you also have to think about the organism you're trying to kill, right? So you want to make sure that the organism is treatable with the compound, otherwise you're just wasting your time. Also, whatever you're trying to treat with the compound, whether that be a table, a carpet, or whatever, you want to make sure the chemical isn't going to destroy it. Because if it destroys it, then what's the point? If there's a lot of contamination, you should probably use more chemical or at a higher concentration. You should probably try to get rid of it as much as possible before you go into the chemical treatment. Time of exposure. This is something a lot of people forget about. In a little bit, we'll show a table, and you'll see that it actually can take up to 10 minutes before the compound kills the organism. Okay? So a lot of times people just wipe something off, and then they, are cool with it. They think it's done. In reality, it takes a little longer than you would think. And then the strength of the chemical, okay, and how well it works is a germicide. So here's that table I was telling you about, okay, and this is broken up into categories based on the chemical agent, okay, and how effective it can be. So we'll start off with chlorine. The most common compound that uses chlorine is going to be sodium hypochlorite, which is bleach, okay. And you can see at 50 ppm, which is about the solution you make to clean, your table and things, the stuff that comes in the spray bottle. It takes about 50 seconds to kill Microbacterium tuberculosis. Okay, so it's relatively effective at that concentration. But when you drop it down to about 0.1 ppm, which is the amount of chlorine found in drinking water, What you notice is that it takes a long time to kill organisms in these solutions. Okay? 3 ppm, which is diluted bleach, you can see for something like hepatitis A, it can take up to 30 minutes. Hepatitis A is a viral infection, affects the liver and causes really nasty kind of gastrointestinal problems and things like that. It's transmitted through the fecal-oral route, and so you would expect, this would be kind of wherever someone that's infected with it, whatever they touch. And so 30 minutes is a long time for something to be destroyed. Ethyl alcohol, this is one of the worst types of compounds. This is the active ingredient in most hand sanitizers. And what you notice is for all these organisms, with the exception of E. coli, it takes a long time for them to work. In fact, 10 minutes is much longer than the ethanol stays on your hands. So what that literally means is that these do nothing. Okay? So when you put hand sanitizer on your hand, you're going like this. All you're doing is moving the organism around. Okay? Because I can guarantee you, 10 minutes, it's not going to stay wet on your hand. Okay? So then you would be fine. And you know what? It's funny. That's how they should sell it, because they probably sell a lot more of it if that's what they told you. But S. aureus is a really easy organism to kill. In 10 minutes, come on, it's not doing anything. Makes you feel better about yourself, but it's not working. Yeah. And that is actually more deceiving than anything, because you smell your hands, you're like, oh, they smell good. I can go ahead and whatever I want. No. Not always the best approach. Peroxide, you can see peroxide is very effective, right? 3%, this is what you would buy, at the pharmacy in the brown bottle. 12.5 seconds, it kills most things. Okay? And in fact, if you jump this up to 10%, which is industrial grade hydrogen peroxide, this can also sterilize. Okay, so it is a very potent compound. Quaternary ammonia compound, this is the compound that's often used in restaurants. Okay, so this is what they use to wipe the table down before you sit down. Okay, and as you can see, 10 minutes. So whenever they wipe the table down, it's a busy restaurant, you go and you sit down, it's all wet. Realize it hasn't been 10 minutes yet. And then ethylene oxide, this is a sterilant gas. This is designed to get rid of things just by, the gas coming into contact with them. This is useful if you want to try to sterilize the whole room, right? So if you have a hospital and someone with Ebola comes in and bleeds everywhere, you can just kick everyone out, close the doors, throw in one of these guys, and in 3 days, everything's killed. Okay? So let's talk about some of these groups and how they actually work. So we'll start off with the halogens. Halogens have literally a halogen group associated with them. Either fluorine, bromine, chlorine, or iodine. By far and large, it's most commonly going to be chlorine and iodine. Okay? Chlorine compounds, as I said, the most commonly used one is going to be household bleach. And these work primarily by denaturing proteins. Okay? And they do this because chlorine compounds are very reactive. And what that means is when they come into contact with another molecule, they will pull that molecule apart. And they do that just by pulling electrons and mixing things up. Okay? So when chlorine compounds come into contact with your microorganism, they go in, they chew up all these proteins, and then the organism dies. These are relatively effective at killing bacteria and endospores at high concentrations. And it can also kill fungi and viruses. But generally speaking, we do not consider these sterilizing agents unless you use them at very, very, very high concentrations. Much higher than the bottle of bleach you buy at the grocery store. Okay? That it will not sterilize. Iodine compounds work in a similar manner, except they tend to be much milder, okay, especially to the skin. So iodine compounds typically are used as an antiseptic. And this is what they'll rub all over you before they cut you open, okay, because it gets rid of most of the organisms on the skin. Phenols. So phenols have a phenolic group. This is a benzene ring with a hydroxyl group, okay? Again, these primarily work by disrupting proteins, okay? However, it is important to note that these are toxic to humans. So for us to safely use these in everyday life, we use them in very, very, very low doses. And what that means is that they aren't actually very effective. An example of a phenol is triclosan. Anyone ever hear of triclosan before? This is the active ingredient that was found in a lot of antimicrobial hand soaps. Okay, if you read the back, it says 0.05% triclosan. So basically no triclosan. And what we found is that this actually is the worst thing to do. Because it doesn't really kill the organism. All it does is induce mutations. And these mutations aren't enough to kill it. Instead, it induces mutations to the point where the organism now is resistant to not only triclosan, but antibiotics. So what we found is this actually induces more problems and more resistance than it benefits. So the European Union outlawed this compound in hand soaps a couple years ago, and about 6 months ago, we are actually starting to do this as well. Finally got through Congress. So general phenols aren't the greatest because they're not well tolerated by anyone. Okay. However, if you take phenols and mix it with a chlorine, you can develop something called chlorhexidine. And chlorhexidine is by far one of the best compounds. Okay? You get the best of both worlds. You've got two phenols or two phenolic groups, and you've got a chlorine group in the middle. And so it can really just go to town and tear up proteins at very low concentrations. These compounds are relatively mild, they're low toxic, and they work very well. And so you can use them on tables, on surfaces, on skin, and they work pretty well. In fact, most of the compounds that are used in the hospital setting are chlorhexidine in nature. It's a very, very common chemical to be used there. Alcohols, we've already talked about them a little bit. Alcohols have a hydroxyl group, or an OH, associated with them. And this means they can kind of denature proteins a little bit, right? They're a little bit reactive. But the important thing to note about alcohols is that these are natural compounds, right? When we talked about fermentation, we said some organisms release alcohols on a regular basis. So what that means, a lot of organisms have ways to get around these, okay? And that's why even at 70% alcohol, it doesn't really do much, unless you light it on fire, then it will kill the organism. Peroxides, so peroxides are denoted by having kind of a free oxygen available, okay? And these free oxygens are very, very reactive. And so what that means is they can go in and they literally just tear the cell apart. And so peroxides tend to be very effective, okay? Especially at high concentrations. At high concentrations, they will kill and sterilize most organisms. However, it is important to note that organic material can contain enzymes called catalysis. And catalysis will break hydrogen peroxide down into water and oxygen, which are inert and not really that deadly to an organism. So if you do have a lot of interfering organic material, hydrogen peroxides are quickly inactivated. Okay? One example of where this happened is where they used concentrated hydrogen peroxide to sterilize endoscopes that were used in colonoscopies. Okay? This works pretty well as long as you get all the shit off. If you don't, you leave the shit on and put it in this guy, quickly gets inactivated and organisms can stick around. And about 2 years ago in UCLA, this happened. They didn't sterilize things properly, and they were transferring all sorts of organisms from one patient to the next. A couple people actually died from it. Okay? So it is an important thing to keep in mind. So usually what will be done is you will use a soap to get rid of most organic material, and then you will put it in something like this to sterilize. Okay? Same goes for a cut. If you've got a whole bunch of dirt in your cut, don't just pour peroxide on there. Those bubbles that you're seeing, that is it being inactivated by the enzyme as well as your blood. So you want to wash it as good as possible, get rid of the blood, any interfering organic material, then put on the peroxide. Surfactants, okay, so surfactants are detergents. So we mentioned before, these work by wiggling their way into the membrane, breaking it up, and making the membrane hydrophilic. The cell then loses its ability to control its environment and quickly dies. Okay? These guys don't work very well. Okay? Again, these are most of the time naturally occurring compounds, and the cell has developed ways to get around them. However, where these come into their own is to loosen the organism up. So a lot of times we use soap not necessarily to kill the organism, but to decontaminate it, okay? Or break it off of the surface and then wash it away, okay? So if you use this in combination with something else, like hydrogen peroxide, for example, it becomes very, very effective, okay? So again, washing your hands isn't really designed to kill the organism. That soap is just there to loosen it off of your skin, and then you wash it down the drain. Heavy metals, so heavy metals like mercury, silver, gold, copper, arsenic, zinc, and so forth, work relatively well at killing microbes. And they do this through oligodynamic action, which essentially means they can disrupt enzymes and their functions within the cell. These work, however, they aren't very practical because they are heavy metals. Okay? However, in some applications, they can be useful. So, for example, back in the day, they used to put gold in your teeth, right? If you lost a tooth, they put a gold in it, or gold film. And what the gold did is not only look cool, it would kill the organism, right? Because gold has the ability of destroying organisms, okay, and slowing its growth. So here's just some examples. You take silver amalgam, which is just silver mixed with some other compound, usually mercury. This is what's usually used in metal fillings in your mouth. Or gold foil. Place that on a petri dish with organism. You can see organism doesn't grow around it. And this works relatively well. However, if you were to let this sit for, let's say a couple weeks, came back, you would see organism growing all right next to it. And that's because they eventually get around it, right? They develop other enzymes, or they mutate, or whatever, and can get around these proteins. So again, not really practical to use. Aldehydes. So aldehydes have what we call an aldehyde group, which is a CHO. It's a C double bonded O. And aldehydes, usually, at least the most effective ones, will have two of these aldehyde groups associated with them. These aldehyde groups are what we call really sticky. That's the technical term for them. And what they do is they can stick to protein very easily. And so what they primarily do is something called cross-linking. So they'll wiggle their way into the cell, and then one of the aldehyde groups will bind one protein, the other aldehyde group will bind another protein, and stick the two together. And when this happens over and over and over again, all the proteins get stuck together in a big mass in the cell, and the cell dies. So these work pretty well. The problem with these is they're very toxic and deadly to humans. Okay? So we don't use them in a regular, everyday kind of basis. But where they do get used a lot is, especially with things like formaldehyde and formalin, which is formaldehyde in water, is in preservation of tissues. Because not only is it going to stop the microorganism from growing because of this cross-linking, it will also cross-link all of the proteins in the tissue and keep the tissue together so it doesn't break apart. Okay? So you can use this for preservation. But again, it's not something I would spray all over you because it will cause cancer and probably eventually kill you. Gaseous sterilants. So this is where you use a noxious or toxic gas. These are usually chlorine or halogen based, and these work by disrupting proteins. Okay, these are primarily used again to sterilize big areas. Okay, they're not used in everyday life, again because they are very, very, very toxic. Okay, so this is something you would use primarily in a hospital setting, where, like I said, you've got a lot of contamination and you just want to bomb the shit out of it and hope that everything. The most common gaseous sterilant is going to be ethylene oxide. Okay? This is a really, really nasty toxic chemical. It's used in chemical warfare to kill humans, if that makes it any clearer. So it is not something you would want to breathe in, or it would kill you pretty quickly. Dyes. So a lot of the dyes that we use for staining our microorganisms, like crystal violet, malachite green, safranin, these are actually relatively potent at killing microbes. How do they do it? Well, they bind to the cell wall, disrupting it, and the cell then dies. So these could potentially be used as a disinfectant. However, the biggest problem with dyes is they are dyes. So they dye things. And so if you try to rub it all over your table or do it on your clothes, it's going to ruin the stuff. Okay? So it's not really that practical. However, back in the day, 1800s, these were actually used pretty often for treatments. Okay, so historically one of the treatments for syphilis was malachite green, and malachite green is the green dye we used in our endospore stain. So you would drink malachite green and hope for the best. Would recommend it nowadays. There's better choices, but it was, worked marginally well. It still gets used in very specific applications. So an example is in fish tanks. So if you have a fungal or bacterial infection in fish tanks, you add a couple drops of Malachite Green and it clears the infection. Okay? But generally speaking, we don't really use these too long. Acids and alkalis, so anything that's really acidic or really alkali is going to disrupt protein, and this will then kill the cell. However, especially with acids, bacteria in particular have developed ways to get around this. So you do have organisms that can live in very, very low pHs, or very acidic compounds. However, if you have an alkali compound, it's much, much more difficult for organisms to survive it. So generally speaking, anything with a pH above 10 is going to kill organisms. Okay? And so a lot of the compounds that we just talked about not only work by using chlorines or phenols or whatever, but they also work by being alkali in nature. Okay? So ammonia, for example, is alkali. Bleach is alkali. So not only does it have a chlorine, it also is alkali and disrupts the protein in their fold. So here we just have a list of some of the different active ingredients, and then some of the more common names for those ingredients that get used all the time. So dimethyl benzyl ammonium chloride, this is a chloride compound as well as a detergent. And this is the primary compound in Lysol. Okay. Sodium hypochlorite, which we have already talked about. This is also known as bleach. It's a halogen and works very well. Triclosan, as we talked about, is a phenol. It doesn't work at all really. And so you can see it was used a lot in antibacterial hand soaps, but it's quickly being phased out. Okay. And then there are other more kind of specific ones, and they work relatively well depending on the situation. Down here you can see sodium chloride, which is kind of like a salt-based item, and you can see in eye drops this works relatively